All right, moving on. Let's do another rational function. We'll look at analyzing the graph of the following rational function, and then we'll sketch it using its characteristics. So as we mentioned in our last problem, our first step is we want to go ahead and factor the numerator and denominator polynomials. So with the numerator, we have a quadratic polynomial written in 2x squared. Of course, every quadratic has two linear factors of x. Of course, x squared factored is x times x. Denominator is another quadratic, and it factors nicely. We've got a difference of squares, x squared minus 3 squared, so it factors to x minus 3 times x plus 3 using the difference of squares property. Now, unlike our last example, this one does not have any common factors. So with that said, I'm going to make a note here. No common factors. All right, there are no holes in this graph. All right, so again, that's something to look for. So down here, we can go ahead and answer. Find the holes of the function, right, as ordered pairs. There are none. Right? Again, no common factors. Now, with that said, let's talk about domain. So domain being all the x values that satisfy this function. That comes directly from our denominator. We know in a rational we cannot divide by 0. So again, we know that x minus 3, right? We know that it cannot equal 0. Just same as x plus 3 cannot equal 0. So as we solve for x cannot equal 3, and x cannot equal negative 3. So domain, right, we were looking at it in a interval form, right? We got negative 3 and 3 as undefined values, which will be the locations of our vertical asymptotes that we'll mention here in a minute. So with that said, let's go ahead and list the domain. So we've got negative infinity to negative 3, negative 3 to 3, and then 3 to infinity. So we have three regions that are formed. So all x values less than negative 3, parentheses, on negative 3, don't want to include it, or all x values greater than negative 3 and less than 3, the middle region of the graph, or all x values greater than 3, 3 to infinity. So there's our domain, has a list of all those x values. Find the zeros of the polynomial. So again, we're finding the zeros. We're going to let f of x, right, equal 0 and solve for x. Right? And with that said, remember now when we find the zeros, we're also finding the x-intercepts, right, for our function. So again, with these real number zeros, but let's go ahead and do that. So we have 2x squared, right, over x squared minus 9. If you want, you can write it in factored form. We'll go ahead and write in our factored form polynomial. All right, we want to set that equal to 0. Of course, as we solve for x, right, we know we're going to clear out the fractions. So we're going to multiply both sides by the LCD. And you notice as we do that, right, we can divide out the common factors of x minus 3 and x plus 3. And we're just left with the numerator, right, equal to 0. So that's true with any rational function, right? We're just setting the numerator equal to 0. So 2 times x, or 2x squared, equals 0. 0 times x minus 3 times x plus 3 is 0. So that implies, as we take our factors, set them equal to 0, we got a 0 of x equal to 0. So there's the 0. Now that implies the x-intercept point. X-intercept is equal to 0, 0. So we know it crosses through the x-axis at the origin in this rational function. All right, let's move on and find the y-intercept, which if the x-intercept's the origin, we know the y-intercept's going to also be the origin. But as we look at that, we're going to let x equal 0, right? Let x equal 0. As we do that, we're going to find the function f of 0. So f of 0, is equal to 2 times 0 squared divided by 0 squared minus 9. As we simplify, we get 0 divided by -9, which is 0. So yeah, our y-intercept, as we knew, right, would be that ordered pair 0, 0. So if the x-intercept's at the origin, of course, that's where the y-intercept or y-axis also intersects. Find the equation of the horizontal asymptote. So remember, to find the horizontal asymptote, we're going to compare the degrees, right, of the two polynomials. So let's go ahead and talk about the numerator degree. So numerator degree of our polynomial, and this problem is a degree 2 polynomial. And our denominator degree is also a degree 2 polynomial. As we look at these two, we got the degrees being the same. So remember, with same degrees, all right, we do have a horizontal asymptote. All right, so again, numerator degree, I'll let that be n, give it a name, and m, reference in the denominator degree, that's equal. So n is equal to m in this example. The degrees are the same. So with that said, that implies the horizontal asymptote exists. And where it exists, all right, it exists, right, at y equal to the ratio of the leading coefficients. So the leading coefficients, well, our numerator polynomial was 2x squared. Our denominator polynomial's leading term was x squared, so its coefficient is 1. So again, these are the ratio of the leading coefficients. Now remember, if our degrees are the same, it's the ratio of leading coefficients. If our degree of the numerator is less than the degree of the denominator, right, we have a horizontal asymptote at the line y equals 0, which is the x-axis. But y equal 2 is our horizontal asymptote. So our graph will flatten out at 2. So it'll be like a magnet. Our graph will converge in on that line. Now it could intersect that line. All right, we're not saying it's an undefined location, but as it intersects it, you'll notice it won't leave that area. As it approaches this line, it gets closer and closer to it. So we'll see the effect of that asymptote in a little bit when we graph it. So it's going to help shape it. Now, vertical asymptotes, remember, come from the zeros of your denominator polynomial. Now remember, we're talking about the remaining factors. Make sure it's reduced. So if you've reduced it, make sure you've done that first. So any factors that cancel out, those are wholes. Any remaining factors, we need those zeros. So as we look at the zeros, we've got x minus 3 again equal to 0, or x plus 3 equal to 0. So yeah, x equal 3 or x equal -3. So our vertical asymptotes, we have two of them. We'll have one at -3, all right, and we'll have one at +3. So they're the two vertical asymptotes. Our graph will go vertical at that location. All right, well, let's go ahead now and build a sketch of our graph based on what we found so far. So sketch the graph, label all the asymptotes. So let's go ahead and build in our x and y axis. Now as we do that, again, we've got, and I'll put them in a different color, here at 3 on the x-axis, it's a vertical. And over here at -3 is a vertical. So I'm going to draw in that undefined location. Graph goes vertical at these two locations. Now, let's go ahead and draw in the horizontal asymptote. And the horizontal asymptote was at y equal 2. So at 2 on the y-axis. All right, we'll draw in the horizontal. And as far as intercepts go, we only found one intercept, and that was the point 0, 0. So we'll plot that one point that we have. We know the graph passed through that point. And that's the only point that we found. Now, let's go ahead and see if our function intersects the asymptote. So let's determine that, all right? Does f of x intersect the horizontal asymptote at y equal 2, right? So that implies, does f of x equal 2? That's our question, algebraically. So we got to find out if that's true. So does f of x equal 2? Well, as we go ahead and set that up, so that implies, going back to our function, right, we've got what? We had 2 times x over x minus 3 times x plus 3 equal to 2. So if you want, we'll go ahead and write it in factored form. Equal to 2. Now, as I'm solving that, again, I'm going to clear out the fraction. I'm going to multiply by the LCD. X minus 3, x plus 3. X minus 3, x plus 3. And, of course, these cancel out. So as we simplify down, we're left with 2 times x, which is 2x squared, equal to 2 times x minus 3 times x plus 3. Well, that gives us, again, 2x squared equal to 2 times what? And over here we got x minus 3x plus 3, which we know is x squared minus 9. We'll go ahead and write that back. So 2x squared equals 2x squared minus 18. As we go ahead and look at it, and that was the original function, right, in this problem. So as we subtract the 2x squared, notice what happens. I'm trying to solve for x. I get 0 equal to negative 18. So false. All right, not true. So that implies no intersection. So it does not intersect. So we know it gets closer and closer to that line. So we'll remember it as we're building it. Now, as we sketch the graph, we do need some points. So I'm going to look at a couple easy points to look at. Now, what happens to the left vertical asymptote at x equal negative 3? And again, I'm going to write in those asymptotes real quick. At y equal 3. Let's see what happens at negative 4. So we're getting an easy value. Any number less than negative 3, we'll find out what happens to the left of the vertical asymptote and, of course, at y equal 3, the horizontal asymptote, where it'll converge on it. So let's go ahead and find that. So our test value, so if x equal negative 4, all right, that implies f of negative 4 equal 2 times negative 4 squared over negative 4 squared minus 9, right? Plugging into our original function, 2x squared over x squared minus 9. And as we simplify, that's 2 times 16 over 16 minus 9. So that's 32. 32 over 16 minus 9, that is 7. So I got 32 sevenths. And of course, 7 divides in 32 4 times with 4 left over. All right, so we have 4 and 4 sevenths. And there it is. There's our point. We could plot that, right? We could use that point there as we're looking at graphing in this function. So negative 4, let's go ahead and plot that ordered pair. Up 4 and 4 sevenths on the x-axis. So right here, right above y equal 3, we have our point. So there's that ordered pair, negative 4, 4 and 4 sevenths. And that's enough now to sketch it. So we know our graph passes through that point, and it gets closer and closer. Without touching, it will never touch, of course, the vertical asymptote, right, because that's undefined. And we've already determined that we'll also never touch y equal 3. It never equals that. So it gets closer and closer and closer and flattens out. Now, based off that information, now we can look at this middle behavior. So we look at what happens in the middle based off these asymptotes. All right, now, with that said, what happens to the left and right of 0, 0? So I might want a quick point to look at, negative 1 and 1. Now, f of negative 1, I'll go ahead and evaluate that quickly. That'll be 2 times negative 1 squared over negative 1 squared minus 9. As we simplify, that's 2 times 1 over 1 minus 9, which is equal to 2 divided by negative 8, which is negative 1/4 as we reduce. So negative 1, negative 1/4, right? That would be a point that we could go ahead and plot real quick. So negative 1, negative 1/4. So we know our graph passes through that point. And same thing at 1, right? We know at 1 we could find a quick point. So what's f of 1 going to equal? That's 2 times 1 squared over 1 squared minus 9, which is what? 2 over negative 8, which is negative 1/4. So over here at 1 on the x-axis, we have the same thing going on. It passed through the point 1, negative 1/4. So we could plot that ordered pair as 1, negative 1/4. So graphically, we got our sketch now. So we know our behavior here between the two asymptotes. So you can see it converging in on the verticals. Last thing to do is figure out what happens to the right of 3. I'm going to use 4 as my test value. So let's go ahead and evaluate what is f of 4. F of 4 would be equal to 2 times 4 squared. So we plug that in, divided by 4 squared minus 9. So that's 2 times 16, which is 32, divided by 16 minus 9, which is 7, which that gives you 4 4/7. So 4 4/7, that'd be a point which we'd go ahead and plot. And we know our graph passes through. And based off the asymptotes, we get closer and closer and closer. It flattens out at y equal 3 and goes vertical at x equal 3. I'm sorry, y equal 2. I shouldn't be saying y equal 3. All right, this horizontal asymptote was at y equal 2. So correct me on that. Converge in on it. But there it is. There's our graph, right, of our rational. So again, using our asymptotes, all right, using our intercepts. We only had 1 in this one. And then some quick test points, just get a little detail to the graph. So that's building a sketch of a rational function. So I hope that helps. Now the only thing we haven't looked at with horizontal asymptotes, we did not have a case where the numerator was less than the denominator as far as degrees. Just remember, if that's the case, it'll flatten out at the x-axis, y equals 0. And we have some of those examples in our notes in our lecture that we did. But those are a couple examples. Good problems there as we're building sketches. All right, so I hope that helps with rationals.